Okay, so we're going to go through some work on exponential and logs today, and today we're going to be converting how to make a non-linear trends into a linear. So you'll probably be familiar with problems involving straight line graphs. So what we're going to do is convert logs, which is exponential relationship, into a linear one. So in short, if we look at this, now both of you recognize this graph, right?
Yeah.
So this is y equal to x squared. It's a curve, and it goes through this origin here. So now if I go through this one here, you will see this is a straight line. This graph, okay, we've turned into a straight line graph. They are the same equation, but we've just changed the scale. So this became a log scale, log x, and this is log y. Can you see this?
Yeah.
So when we change the scale, okay, and we plot the points, it makes it into a straight line graph. Because these values here, like log 2, log 4, log 6, they're not going with the same scale, are they? These are log scale. So you're probably aware of this whole COVID-19 illness. If you were to look at the growth or number of cases, it makes a exponential growth, right? But if you change the scale into a log scale, it actually fits into a straight line like this. So there's an interesting video you could have a look at on the Vox YouTube channel. Anyway, so that's what we want to do. We want to make a non-linear graph into a linear one, changing the scale. So let's start off with this equation. Now we know that this is a exponential graph. If we take log on both sides, we could write this like this. Log y equal to log ax to the power of n. And using log rule, you could write this, because they multiply log a times x to the power of n, you could just write log a plus log x to the power of n. You understand this from the log rule, right?
Yeah.
Okay. Now using the log rule, we could bring the power down. So log y equals to log a plus n log x. Now what do you think this equation looks like?
Straight line graph.
Yeah, it looks like a straight line graph, doesn't it? Yeah, it looks something like this, y equals to mx plus c. So in this case, our y would be log y, okay? And the mx, well, there's n log x, so the m would represent the n log, the n. Does that make sense?
Yeah.
And the c would be the log a. So we could already see something that would have been an exponential growth, a curve. We could write it in a linear form by changing the axis. So if we have ax to the power of n, we could write this in that form. Now notice this is ax to the power of n. Later on we're going to look at n to the power of x. So x will become the power. This time n is the power. So there's slight difference. So here we have a population of 5 major cities in the UK, with the exception of London, and we rank them in order of the population. So we've got Birmingham, Leeds, Glasgow, Sheffield, Bradford, and rank R would be 2 for Birmingham, that's the second biggest city, and 3 for Leeds, and so on. And this is population size. So we've got a 1,730,000, 620,000, 530,000, 480,000. So we're going to see how we could make this, which we know is going to be a non-linear relationship. Okay, and we are told that this can be modeled by this formula, P equal to A R to the power of n. Okay, so if you just write down P equal to A R to the power of n for now. And then we're going to look at what the graph looks like. So for now, don't worry about copying down the table. We're going to copy the table in a minute, okay?
Okay.
I just want you to write down this equation, P equal to AR to the power of N. And if we plot this, so you'll see there's P for the population, R for ranking, and this is a linear scale. You could see it's making a curve. Can you see?
Yeah.
It's a decay, but still a curve. Now, if we had rank 1, which would be London, it would be like somewhere way up there. You know, probably be 7 million, I think it is, 6 or 7 million. But still, it follows the curve, right? So once we complete the table, we get this value, and this is just coming from typing log 2 on the calculator, log 3 on the calculator, and so on. So now what we're going to do is plot the graph. So this was the nonlinear relationship when we had the scale P against R. Now we've got log P and log R. So what we need to do is plot the graph with log R here and log P there. So once we plot the point and just draw a straight line, you can see it fits in perfectly. We get this line going down. Okay, on part C, it says use your graph to estimate the values of A and N to two significant figures. And so because it's going to be a linear relation, we're going to look at the formula. So remember what I said about the log rules here. We could just write this in that form using the additional law and then bring the power down. So this can be converted into this form. Is that okay?
Yeah.
Okay, so now what you will see that log A is the constant, you know, the y-intercept value, if you like, right? And n is the gradient of the line, okay? Because n log x, remember log x, they're together, so n is the gradient of the line. So all we have to do now is read from our graph what value of log A is. Remember, this is log graph, log P and the rest log R. So if I read off the value, I make it out to be 6.2. Is that okay?
Yeah.
So now what we have to do to work this out is rewrite this in exponential form. And now you know this from previous lesson. To write this in exponential, by default, the base is 10. So you could write 10 to the power of 6.2 equal to 8. Now you remember this from last lesson, right?
Yeah.
And so if you type that in on the calculator, 10 to the power of 6.2, it gives you the following. So there we go, we got our A value. So now for N, well, that's just the gradient of the line. So you could just simply take any 2 points and just do rise over run. So when you do the gradient between 2 points, it should give you approximately n equal to minus 0.67 or ish. So now we have the gradient n and we've got the a value. We could simply substitute into this formula. So p is equal to this r to the power of minus 0.6. So what we had here, okay, we just made a formula for it. P equal to 1.6 to the times 10 to the power of 5 times r to the power of minus 0.67. So do you guys understand that?
Yeah.
Okay. So we're going to look at a slightly different situation now. So we have the power this time, which is the x. So again, we're going to use the log rule, take logs on both sides, and then simply just split them up, bring the power down, and this looks very much similar to y equals mx plus c once again. So same as before, our y would be log y, but this time bit careful, the mx, your m is going to be log b. So that's the difference. Notice before you had your m as n, but this time your m is log b. Do you understand why?
Yeah. Yeah.
With one, can you see it?
Yeah.
And because it's talking about mx, that's the x, so this must be the m. And simply c would equal to log a. So if you have x as the power, then you write this as log y equal to log a plus xb. So these are the two separate equations. In this example, to get linear relationship, we plot log y against log x, like we did just a little while ago. On this example, we plot log y against x. So that is the difference between how we plot these two. This time, we'll look at this example here. So graph shows the growth of population of bacteria p over a period of time t, and we are told the gradient is 0.6, and it cuts the log p axis at 2. Our scientists suggest that this growth can be modeled using this equation, p equal to ab to the power of t, where a and b are constants to be found. So we're going to write down the equation of the line, and we're going to use our answer to part A, or otherwise to find the value of A and B to three significant figures, and we want to interpret the meaning of constant A in this model. So first of all, this can be written in this form, because we've talked about, because you got to the power of t, we could write this equation like that. Is that okay?
Yeah. Yeah.
And because we know what log a is 2, so we could just simply replace log a with 2, and we also know the gradient of that line, which is log b, which is 0.6, so log p is equal to 2 plus 0.6t. Is that okay?
Yeah. Yeah.
So that's it, so that's part A. So if we rewrite this using the exponential and log rules, you could see that this is base 10 because that's a default position. So it's going to be 10 to the power of this equals to p. Can you see this?
Yeah. Yeah.
So now, using the indices rule, because there's a plus here, we could write 10 squared times 10 to the power of 0.6t. And 10 to the power of 0.6t, again using the indices rule, we could write in a bracket like this. And 10 to the power of 0.6, we know is 3.98. So this is the equation for p. So then we have it. We are asked to find the values of a and b. We've got the values of a and b, so p is equal to 100 times 3.98 to the power of t. So a must be 100 and b must be 3.98. Now let's see. It says interpret the meaning of the constant a in this model. So a, if we let t equal to 0, 3.98 to the power of 0 is 1, so p would simply equal to 100. So which means A is representing the initial size of the bacteria. So 100 gives us the initial size of the bacterial population.